Thank you. People have been observing the night sky for millennia, and from ancient times they always noticed that some of the stars in the sky stay at the same place relative to each other, and we have the familiar constellations, and some stars wander, what was called wandering stars, and today we understand these as the planets of our solar system. And some stars appeared and then disappeared, and the Chinese astronomers called these guest stars. A very notable example is from the year 1054. In the spring of that year, a star appeared in the sky and was visible during the daylight. It brightened until July, at which point it was brighter than everything in the sky except the sun and the moon. This star then started to fade, and after being visible for a few months during the daylight, it was visible only during the night, and 2 years after it appeared, it disappeared completely. And the Chinese astronomers wrote down exactly where in the sky they saw this star appear. And we can use modern technologies such as the Hubble Space Telescope to look at the exact same point in the sky. And when we do that, what we see today is the Crab Nebula. This is a cloud of gas about a little bit over 6,000 light years away from Earth, and its size is a few light years across, which fits for a material flying at a few thousand kilometers per second for almost 1,000 years. This is quite fast, and the way we understand this is we think there was a star there, a regular star similar to our sun, but a bit more massive and larger, and then the star exploded. And what we see here is the inside of the star thrown into the interstellar medium. This is a very interesting nebula, so we point at it everything we have with modern technologies. And besides the visible light, which we can see with our eyes, we also observe the Crab Nebula in other colors, which we cannot see with our eyes. And I want to note mostly the radio and the X-rays which we see in this nebula. And these tell us that there is something inside the center of this cloud of gas. And this is the Crab pulsar. At the very center of this picture, there is a very dense star, a neutron star, which is more massive than our sun, but it is only a few kilometers in size. This means it is very dense. It is so dense that if we take a teaspoon of material from it, it would be about 10 million tons. And the way we understand this, how can such a star exist, is that the inner part of the star collapsed into itself and was compressed and became a neutron star, while at the same time the outer part of the star were thrown off, and this causes the rest of the gas that we see. So the Crab Nebula is of course unique, but there are several other nebulae similar to it in the galaxy. So here are 4 other examples where we look with modern telescopes at places in the sky where astronomers of ancient times saw a star appear and then disappear. At the top left, we see what we think are the remains of a star whose explosion was observed on Earth in the year 185 AD, almost 2,000 years ago. And this is the oldest recorded supernova in human history. In the bottom left, we see the remains of an explosion that was observed on Earth in the year 1006. This one is just a little bit farther away than the Crab Nebula, and it is thought to have been the brightest astronomical event seen on Earth. The one in the bottom right was observed, not the gas cloud, but the star, the exploding star, was observed in 1604, just a little bit before the modern telescope got into use. And this was the last supernova, the last exploding star which we observed from Earth, which exploded in our galaxy, in the Milky Way. So we think all of these clouds are what remains from stars which exploded and threw out all of their material into space. But how can we know that for sure? So while we have not seen another supernova in our galaxy since 1604, we have seen many supernovae in neighboring galaxies and farther away. The closest one to us was observed in 1987, and this was the first time where we clearly saw the star that was there before the supernova. So on the right there is a picture which includes the star, and this is a picture from before 1987. So after the supernova was observed on Earth, astronomers went back to the archives and looked at pictures of the same region in the sky, and they identified clearly that there was a star there, and this star exploded. So this is another part of the story of exploding stars. We know that there is a star there, and then it explodes. So this was in the Large Magellanic Cloud, which is a neighboring galaxy, which we can see in the southern hemisphere. So we look here at the night sky of the southern hemisphere. There are the small and large Magellanic Clouds, which are neighboring galaxies, and we're zooming in to a region of this small galaxy where we saw this explosion. So this is relatively nearby, but not that nearby. It's more than 160,000 light years away. And there, this little ring, this is where the star exploded. And because this is the most nearby supernova in modern times, it has been observed constantly since then. And we can see what happens over time, over the years. That the part in the middle is the star which exploded, and around it there is a ring which is lit up by the exploding star in the middle of it. So these are the images from 15 years of observations of that point in the sky. We see in the beginning the bright explosion, and it fades over time, but the ring around it brightens. And this was the first time we saw clearly a star which exploded, but we saw several more after that. And we also saw many, many supernovae since then. Also before, but much more after. In modern times, in the 21st century, we are using automated telescopes and computers to find these exploding stars. And since the beginning of this century, there have been hundreds of supernovae observed almost every year. Now, most of these are found automatically with computers, but there are still some chance discoveries similar to the way that supernovae were detected before we made the detection automatic. And a nice example is the supernova from 2014 called 2014J. The letter J means that it was the 10th supernova detected in that year, and it was detected in January, so early in the year. And this is a nice story because it was detected during an undergraduate class at the University of London Observatory. So there was a bit of clear sky, and they took the opportunity to look at this galaxy, and they noticed that something is different. It seemed that there was something different. And they took an old picture of the galaxy and compared it and saw that there is something new. And this is an exploding star. So this is quite a recent example, but it is not the typical example because most of the stars in supernovae we see are farther away, and we cannot see them as clearly as the one from 87 or this one. But we have seen several tens of supernovae where we know what was the star before. Since 87, there have been a few other detections, and we can ask what kind of star explodes and why. So, to understand what happens at the end of the life of a star, we first look at what happens during their life. This is a diagram which shows different kinds of stars that we know. So, this is their brightness and their temperature, which determines their color. So we have the red stars on the right, and we have the blue and hotter stars on the left, and the luminous stars are the giants on the top, and there are also faint and hot stars which we call white dwarfs, which are on the bottom left. And for about 30 of the supernovae we have observed, the star that was there before the explosion was a red supergiant, so a massive giant red star. For several others, it was a yellow or blue giant. And this makes sense because giant stars are much more luminous, so we have a much higher chance that when we go to the archive after the supernova and look, we'll find a bright star if it was there, so that would be a giant. And the red stars are more common, and that makes sense that most of the cases would be red giant stars. We think that other types of stars can explode as well, but for example, if a white dwarf would explode and we went back to the archive, we would not see anything there because a white dwarf is a very faint star. So only if it exploded very nearby, then we would be able to see it before it explodes. So why do stars explode at all? During their life, stars live in a balance of pressure and gravity. They are massive and they pull themselves inwards, and this gravitational force is balanced by pressure from the hot gas inside the star. They are luminous and emit a lot of energy, so they have to supply this energy to keep the balance. And this energy is supplied by fusion in the core, mostly fusion of hydrogen into helium, like our sun is doing right now. And we can ask what will happen when the star runs out of fuel. It burns all of its hydrogen in the core and cannot supply any more energy. So what will happen? When there is no more fuel to burn in the core, gravity wins, and the core starts to contract into itself. This causes the core to be more compressed and to heat up, and the outer parts to expand, and the star becomes a red giant. At some point, the core is hot enough to now fuse helium into carbon. So the star still has some more fuel, and it continues its life as a red giant. So we see here, the star first burns hydrogen into helium, then it runs out of hydrogen, and it has a helium core. It expands into a red giant, and then it starts fusing helium into carbon. And for most stars, this would be the end. They would never be hot enough to fuse carbon. And the core, which is made of carbon and oxygen, would be left behind as a white dwarf, and the outer parts will be blown off. But for more massive stars, the inner part becomes hotter, and they can continue fusion, and they fuse carbon and oxygen into silicon, and they fuse silicon into iron. But they cannot fuse iron. It is not a fuel. They cannot get energy from iron. And then, after the star burns up all the silicon it can, the iron core becomes unstable, it loses pressure, and gravity wins, and it collapses into itself. And this happens in 1 second. And then the iron core becomes a neutron star. So the fates of stars are determined by how massive they are. So we have the most massive stars, which are blue when they are born and very hot, and they live their lives faster and hotter than regular stars, and then they explode as supernova, leaving behind a neutron star or maybe a black hole. And we have stars like our sun, which burn hydrogen into helium and helium into carbon and oxygen, and then they become red giants, and then they slowly blow off the gas in their outer parts and become white dwarfs. A white dwarf, left alone, will just cool and fade away, and nothing very interesting will happen. But if it interacts with the second star in some way, then it might explode. And we think that there are 2 different ways that a star can explode and make a supernova. And 2 nice examples are these: the supernova from 1006 and the supernova from 1054. So I said earlier that in the center of the Crab Nebula we see a pulsar, which is a neutron star core. But in the center of the remnant of supernova from 1006, there is nothing. So we think it was a white dwarf which completely exploded, leaving behind nothing. And while these massive stars end their lives in these dramatic explosions, which are quite spectacular, it doesn't mean that the regular stars, like our sun, do not have spectacular ends. So even though they blow off their gas quite slowly compared to a supernova, they still make these nice images. These are called planetary nebulae, which are clouds of gas, which are the outer parts of a regular star or a red giant, which are thrown off into space. And in the middle there is a white dwarf. So this is the phase between a star being a red giant and becoming a white dwarf. And maybe if there are 2 white dwarfs in the middle of a planetary nebula, they might somehow explode, maybe collide into each other and cause an explosion of a supernova. And then we'll have a supernova exploding inside the planetary nebula. And maybe it will look like this. But I'm just guessing, I don't know. This is G1.9 plus 0.3. And this is the most recent supernova from our galaxy. This cloud is about 110 years old. So I said earlier that the last supernova observed from Earth, which occurred in our galaxy, was in 1604. So why didn't we see this one? This supernova remnant is located in the Sagittarius constellation, which is the direction of the center of the galaxy, where there is a lot of gas and dust. So it exploded behind a lot of stuff, which made it invisible to us from Earth. But we can now look at it with modern technology, and we can see this cloud of gas. These supernovae explosions and planetary nebulae, which throw out all of the material of the stars and the material that the stars make, they exist for hundreds, thousands of years, and then they just disperse into the interstellar medium. And in this way, they complete the life cycle of stars. So we have stars forming from the interstellar gas, and if they are like our sun, they will live for billions of years, become red giants, and blow off their outer parts as planetary nebulae, leaving behind a white dwarf. And if they are very massive, they will live for only a few millions of years, 1,000 times less than our sun and similar stars, become massive red supergiant stars, explode as supernovae, and leave behind neutron stars or black holes. And all of the material that they throw off is taken back by the interstellar medium. And from this material, new stars and planets are formed, like the sun and Earth, and us. So in the end, we are made of star stuff. So, thank you.